Swayam Prabha. Digital India. Educated India.
So today we start a new chapter. This is called inner product spaces. So far we have studied how to solve system of linear equations by using Gauss elimination, and we know the algorithm to find all solutions of any system. Yeah, we also know how to test whether a solution exists, and if the solution exists, how to find a particular solution, how to find fundamental solutions of homogeneous system of linear equations. And then we introduced vector spaces. The purpose of introducing vector spaces was that in a matrix, with a matrix, we have four very basic subspaces which are used in applications: the row space of a matrix, the null space of a matrix, the column space of a matrix, and the left null space of a matrix. So these four subspaces, yeah, they are interrelated, and one interrelation we have already found, which is the rank nullity theorem. Yeah, the rank nullity theorem. We have done it for linear transformations, we have done it for matrices, but for matrices it says that we have the row space of the matrix and the null space of the matrix. Yeah, these two spaces, they are living inside the domain. Okay, and the column space of the matrix is living in the codomain, and the left null space, okay, left null space is really the null space of A transpose. Okay, and we showed that the dimension of the row space, which is called the rank of the matrix, and the dimension of the null space, okay, which is called the nullity, yeah, they add up to the dimension of the whole space in which they are living. Yeah, dimension of the row space and dimension of the null space is equal to dimension of the space in which they live, and which is the number of columns of A. So this is the rank nullity theorem, and we also proved if you have two subspaces, then we know the dimension of the sum of those two subspaces. Yeah, the dimension of the sum of the subspaces. So we did this, that if I have a big vector space V and we have two subspaces, yeah, W1 and W2, then their sum lives inside V. The sum of these two subspaces is really the sum of all the vectors V plus V, where U is in W1 and V is in W2. Okay, and we proved this formula, that dimension of the sum, is equal to the sum of the dimensions minus the dimension of the intersection. So if you apply this formula on the null space and row space, it says the dimension of the sum of the null space and row space is dimension of the row space plus dimension of the null space. Yeah, but that is already equal to the dimension of the whole space, and therefore this intersection has to be 0. Okay, this intersection is actually 0. The row space of the matrix and the null space of the matrix, they intersect only in the 0 vector. Okay, and the null space of A is collection of all vectors, so that Ax equal to 0. But Ax equal to 0 means, yeah, I write the row vectors of A. There are m row vectors of A, and x is a typical vector in the null space, and this is equal to 0. So this means that A1 dot x equal to 0, A2 dot x equal to 0, etc. So therefore, every vector in the null space if I take any vector in the null space, then it is perpendicular to every row vector. Is that clear? Yeah. Every vector in the null space is perpendicular to every vector in the row space. The rows, they are perpendicular to the rows, and if a vector is perpendicular to two vectors, it is also perpendicular to any linear combination. X dot, say alpha ai plus beta aj, yeah, this is equal to alpha ai dot x plus beta aj dot x, but x is perpendicular to ai and x is perpendicular to aj, so this is equal to 0. That means every vector in the null space is perpendicular to every vector in the row space. So if we are living in three-dimensional space and my row space is a plane passing through origin, let's say xy plane, the null space has to be perpendicular. It has to be all vectors on the z-axis. This is forced. The null space is forced to be the z-axis if the row space is the xy plane. This is because of the relation between null space and row space, that the dimension of the null space and dimension of row space, they add up to the dimension of the whole space. We are in three-dimensional space, so their sum of their dimensions is 3, but then there is nothing common except the zero vector in the null space and row space. There's only one vector which is common between them, namely zero vector. And every vector in the null space has to be perpendicular to the row space. So if the row space is xy plane, then the null space has to be the z-axis. Okay, so there is geometry going on behind these subspaces associated to a matrix. Yeah, that's the relation between null space and the row space. And if you go to the right, that is go to the codomain, then we have the column space and the null space of A transpose. Column space of matrix is really the row space of A transpose. So it's the same argument says that the other two subspaces, namely column space of A and the null space of A transpose, they are also intersecting only in the zero vector. The column space of A and the null space of A transpose, they also intersect in the zero vector only, and every vector in the null space is perpendicular to every vector in the column space. Yeah, so the two subspaces, row space and null space, they are perpendicular, they span the whole domain. Yeah, similarly the column space and null space of A transpose, they are perpendicular to each other and they span the whole codomain. Yeah, so we want to now introduce these geometric notions which we already observed among the row spaces and null space, etc. of a matrix. We want to introduce in an arbitrary vector space. Yeah, so dot product is known to us for vectors in Rn, and we want to extend this to arbitrary vector space. Okay, and the purpose is to introduce geometric notions. So length of a vector is a geometric notion. Angle between vectors, yeah, that's a geometric notion. And in your electricity and magnetism, you deal with lots of vectors, but in order to make measurement, you have to take the length of the vector. You want to know angle between vectors to calculate actual force applied to some moving particle, because we know that when a force is applied to a moving particle, only the component of the force which is in the direction of the movement of the particle is responsible for the motion. The other component, which is perpendicular to the direction of the movement, has no effect on the motion of the particle. So we need to decompose vectors as sum of two perpendicular vectors or sum of three mutually perpendicular vectors in R3, etc. So in vector spaces, we want to now introduce geometric notions, and that is made possible by introducing a concept called inner product, which is analogous to what is dot product. Yeah, we will extract the fundamental properties of dot product and make them axioms and say that any operation between vectors in a vector space which satisfies those axioms of dot product are also satisfied, then it will be called a inner product space. Yeah, so let us start introducing inner product space. Yeah, So using the concept of inner product of two vectors, which is analogous to standard dot product of vectors in Rn, we can introduce geometry concept. And we will see that these geometry concepts are very useful to analysis of data. So curve fitting and data analysis is done by using these geometric properties of a vector space, vectors in a vector space. Yeah. So towards the end, I will show that if you are given certain data, we want to understand what is the law behind that data. Yeah. So whether the data fits on a straight line or the data is fitting on a parabola or a hyperbola, etc., etc. Okay. So these problems arose in mechanics, celestial mechanics, because scientists were analyzing the orbits of celestial bodies, and they wanted to understand what is the exact nature of the orbit. And you have studied Kepler's laws. The Kepler's laws say that all the planets move in elliptic orbit. So how did Kepler, see this? So he collected data and then he tried to fit the equation of a ellipse into the data. Okay. So you plot some data and then you can guess that it is turning out to be elliptic orbit, but then you have to prove that it is really ellipse. Okay, and then you observe some more data, make predictions, and etc. etc. So natural phenomena and also applications nowadays in artificial intelligence and data analysis, we have to do a lot of curve fitting. Okay, yeah. To do curve fitting, we will see that what we are learning in this chapter is very essential. It is foundational in nature. How to do curve fitting in a data. So that I will explain after we develop little bit theory of inner product spaces. Okay. Yeah. So for now, rest of the course, we will use the field of scalars will be either real field or the complex field. And when I have A in F, we will write A bar as complex conjugate. Yeah, A bar will be used for complex conjugate. Okay, and if I have a matrix A where the scalars, the entries of the matrix are taken from this field, which can be real or complex, by A star we mean conjugate transpose. So if A is equal to Aij, then A star is obtained by taking the transpose and then take the complex conjugate of every entry in the matrix. So first take the transpose and then take the complex conjugate of every entry in the matrix, and this is called the conjugate transpose of a given matrix. Okay. Yeah. So suppose V is a vector space over a field F. F could be real, F could be complex, but you fix this F. Once you say F, it is fixed. Okay. An inner product on V, okay, an inner product on V, okay, is a rule which to every ordered pair of elements of V associates a scalar denoted by UV within these brackets. Okay. So I'm not writing u dot v because dot is reserved for usual dot product of vectors. Okay, so we write this bracket uv. This is a notation taken from quantum mechanics. Yeah, we use all kinds of inner products in quantum mechanics, and the formula for inner product can change from one vector to another vector space. So we have this notation u comma v within brackets. So a rule which associates a scalar to every ordered pair of elements, yeah, it is called inner product if the following axioms are satisfied. So take any three vectors and take any scalar. Okay, then the inner product of u and v should be the complex conjugate of inner product of v and u. So it is not a symmetric operation. Yeah, it depends on the order in which you take the inner product. Okay, it is order sensitive. So inner product of u with v is complex conjugate of inner product of v with u, and this is called conjugate symmetry property of the inner product. Then the inner product is linear in every component. Inner product of u and v plus w is inner product of u with v, inner product of u with w. And if you use the first axiom, it will imply that it is also linear in the first component. So it is bilinear operation. It is linear in every component. Okay, when you add vectors, addition of vectors is respected by inner product. This is called additivity. Then, then for scalars, there are two rules. If I scale the vector v here, then this c comes out. Okay, this c comes out. So this is called homogeneity. But if I take say c times u, and then take the inner product, this will be equal to by conjugate symmetry. This is equal to v c u bar. Okay, and this is equal to c v u bar bar. This is equal to c bar u v. So if I take scalar in the first component, its conjugate comes out. So this is a consequence of this first condition and this condition, that scalars in the first component, if I scale a vector in the first component, then that scalar comes out of the inner product with a conjugate sign. Okay, it becomes conjugate. But if I scale the second vector in the inner product, then that scalar comes out, not its conjugate. The last property is VV, the inner product of V with V is bigger than or equal to 0. This is one part, that VV, the inner product of a vector with itself, is a real number, is a consequence of this axiom. Because if I put U equal to V here, then this number is its own conjugate. So it must be real. But this says something more, that this is bigger than or equal to 0. Yeah, inner product of a vector with itself is bigger than or equal to 0, and it is 0 if and only if the vector is 0. So this is called positive definite property. So there are 4 properties that we are demanding. If you have an operation between vectors, like we know addition of vectors is one operation, then I can multiply a vector with scalar, that is another operation on vectors. Now we are introducing an operation between pairs of vectors. So conjugate symmetry, that is the first axiom. It is bilinear, it is linear in every component. But then scalars come out as complex conjugates if that scalar is in the first component, and it comes out as itself if it is in the second component. Inner product of a vector with itself is always non-negative. It is 0 if and only if the vector is 0. So these 4 properties have to be satisfied with an operation on vectors, pairs of vectors. Then and only then we say it is an inner product. Okay, so an inner product space is a vector space. So already I have a set which is a vector space, and if we introduce an inner product in that vector space, it is called an inner product space. Okay, so it's called inner product space. So so as I said, VV is always real. In fact, it is bigger than or equal to 0, and CU comma V, C bar U comma V. Keep that in mind. This is a common mistake in exam, that C comes out as C. No, C comes out as C bar. Okay. All right. So let us look at some examples. Yeah. So first look at the common example of Euclidean space Rn. Okay, Rn. Take 2 column vectors in Rn. They have n components. They are real numbers. Standard inner product on Rn is simply sum of xi, yi. Okay, but this can be written in terms of matrix product. V and W are column vectors. So if I take V transpose, that's a row vector, and I multiply this row vector with this column vector, I get 1 by 1 matrix, and that is precisely the dot product of V and W. Okay, so inner product of V and W I am writing as V transpose W. Yeah, so to avoid all these xi, ya, yi, etc., this is a compact notation that if I regard V and W as column vectors, then their inner product, the standard inner product, which we call dot product, is V transpose times W. So it is written in terms of matrix product. Yeah, let's look at another example. Yeah, in Cn, now my vector space is complex vector space Cn. Okay, then inner product of W, these are now vectors with complex components, and we just copy this notation. V transpose W, So the role of V transpose is played by the conjugate transpose. So V star, okay, V is a column vector, V star is a row vector. How to get V star? First make this as a row vector, that is take the transpose of V and then take conjugate of every entry, that is my vector V star, and then multiply this row vector with this column vector W, and this is summation xi bar Vi yi. So this is the inner product in Cn. Cn thought of as a complex vector space. Okay. Now let's relate it with what we already know. So in particular, suppose I take n equal to 1. Then it is simply the set of complex numbers. The set of complex numbers over itself is a one-dimensional vector space. Yeah, it's a one-dimensional vector space. So suppose z equal to x plus iy. That's an element in C1. C1 is same as C, and we know that absolute value of this complex number is square root of z bar z. But z bar z, by our this definition of standard inner product in Cn, is simply the inner product of z with itself. Okay, so z bar z is x minus iy, x plus iy, and that is square root of x square plus y square, and that is the absolute value of z. Okay, so therefore absolute value of a complex number is simply square root of the inner product of that complex number with itself. Okay, standard inner product of Cn between two vectors V and W is V star of W. Okay, and it is copied from the dot product in Rn. So Rn becomes a inner product space, and Cn also becomes an inner product space. You can go back and check those 4 axioms which I wrote. Yeah, 4 axioms have to be satisfied. Yeah, it is bilinear, then conjugate symmetry, and then it is positive definite and homogeneity. Okay, so those 4 axioms can be checked for both these operations and see that V transpose W or V star W, they introduce an inner product in Rn and Cn, so they are inner product space. Standard addition of functions and scalar multiple of functions, they form a vector space. So look at all functions on the closed bounded interval which are real valued functions. Yeah, these are all real valued functions. So this is the vector space which is written by C01. This is the vector space of all functions from closed bounded interval 0, 1 to the field of real numbers, and this is continuous function. Take all continuous functions, then we can add them. We can take scalar multiple, and we know that sum of two continuous functions is continuous on this closed bounded interval. Scalar multiple of a continuous function is also continuous. Yeah. So this is a vector space. You can go back and check those axioms. But now let's introduce an inner product. Yeah, let's introduce an inner product, which is actually copy of the standard dot product. Okay, if you think deeply about this, it is nothing but continuous version of the discrete dot product that we already know in Rn. C01 is infinite dimensional vector space. Yeah, we have seen C01, there are so many functions like sine x, sine 2x, cosine 2x, exponential functions. Yeah, these are all continuous functions on closed bounded interval. So it's an infinite dimensional vector space, and in this infinite dimensional vector space, analog of dot product is integration. So take two functions f and g and then integrate on this closed bounded interval 0, 1, take the product and integrate. Okay, this is continuous version of the discrete product. Integration is analog of infinite sum. Okay, so this is copied from the usual dot product definition, that inner product of functions is integral from 0 to 1 ft gt dt, and you can check the 4 axioms which are just coming from definition of how we integrate functions. So this is an inner product space. C01, the space of all continuous functions on this closed bounded interval, any closed bounded interval. We can consider functions on any closed bounded interval because we need this integral to be a number. Okay, so if I take continuous functions on closed bounded interval, they are bounded. those values are bounded from below and above, and so this integral will always give you a number. Okay, we want the inner product to be a number which is subject to those 4 axioms. Yeah, so in order for a number to come out of 2 functions, I am integrating on a closed bounded interval. Okay, so C01 becomes an inner product space. Yeah, all right. Now let me show you that there is really nothing special about the standard inner product. In fact, there are infinite variety of inner products. If okay, on a vector space, if I can find one inner product, I can find infinitely many inner products on the vector space. How do we do that? Okay, so this is a method. Let B be a non-singular matrix. Non-singular is same as invertible. This is another word for invertible matrix. Take a non-singular matrix and take 2 column vectors x and y in Cn. Okay, x and y in Cn. Now introduce this inner product of x and y to be x star b star by. So B star is the complex conjugate of B. It's an n by n matrix. Yeah, and so By, and so B star B is a n by n matrix, and so I can multiply. But this is x star B star is nothing but Bx star and By. Okay, and Bx star By is nothing but the standard inner product of Bx and By in Cn. Yeah, Bx star By is this dot product of vectors in Cn. When we take vectors in Cn, their dot product is taken by you multiply components, but the components of the first vector have to be taken as their complex conjugate. Okay, so when I write Bx dot By, keep that in mind. It is not the dot product in Rn. It is the dot product in Cn. So we say it's a Hermitian inner product. Okay, when we have to introduce complex conjugate. So Bx dot By is nothing but, in matrix notation, Bx star, which is a row vector, and By, which is a column vector. This is my definition of inner product. So given any non-singular matrix, any invertible matrix I take, okay, I can introduce this inner product with the help of B. So if I keep on changing B, I will get infinite variety of inner product. You can check that this is an inner product, because this satisfied. This is the standard inner product, Hermitian inner product in Cn. This Bx dot By satisfies the 4 axioms, and therefore this new inner product also satisfies the same axioms. Okay, so as you vary this invertible matrix B, you get more and more inner products in your vector space. Yeah, okay. So now let's look at vector space of n by n complex matrices. They form a vector space, and the dimension is n square. This is a n square dimensional vector space. I take two matrices, A, the jkth entry is A jk, and B, where jkth entry I write as bjk. And I want to introduce, in this vector space of n by n matrices, I want to introduce an inner product. Okay, how do we do that? Well, this is the intuition behind this, that if I take a square matrix, it has n square entries. Okay, so I look at the first row vector, I look at the second row vector, and so on. There are n row vectors. Each one of them has n components. So when I line up these row vectors, I will get a point in n square dimensional space. Yeah, there are n square entries in this matrix, n by n matrix. So I can arrange these n square entries row wise or column wise. Okay, but fix a method of arrangement that these n square matrices, the n square entries will be arranged, will give me a vector in n square dimensional spaces, a point in n square dimensional space. So every n by n matrix is represented by a single point in n square dimensional space. Okay, and there we know how to take inner product in a complex space of any dimension. So convert your matrices into points in Cn, and then take the Hermitian inner product. That is the inner product of matrices. Okay, but this can be written very in a compact way by saying that the inner product of these two matrices is the trace of AB star. Okay, it is trace of AB star. So Hermitian inner product of two vectors with n square component is this. Yeah. So this is simply trace of AB star. You can check this right hand side is simply trace of AB star. Okay. So yeah, I need to change this a little bit. Yeah. So earlier the when I had two vectors in Cn, I declared the inner product to be V star W. So if you want to keep this property, then I have to take A bar and this. So this will be A star of B. So take trace of A star B, that is the inner product of two matrices. And with this, it becomes the space of square matrices becomes a inner product space. Okay. Yeah. Yeah. So what do we do with the inner product? Well, we want, as I said, we want to introduce geometric notions in our vector space, and fundamental geometric concept is length of a vector. And then another concept is angle between vectors. Another concept is when two vectors are perpendicular. So we want to introduce these notions using the formula for inner product. So we have a vector space. It could be space of matrices. It could be space of functions. It could be space of complex vectors or real vectors. But we are given fix an inner product. Using that inner product, we want to define length of a vector. And the idea is taken from the formula for absolute value of a complex number. Absolute value of a complex number, z equal to x plus iy, square root of x square plus y square, which is square root of the inner product with z. Okay, so we will lift that definition and introduce length of a vector in arbitrary inner product space. Okay, yeah. So I'll skip this part. You can read this. So given an inner product space V, take a vector in V, we define its length or norm. Norm is also used. Okay, norm is also used because length means the usual length. So when we have an abstract definition of length, we usually say norm of a vector. So norm of a vector V, this is the notation in double bar. It is square root of inner product of V with V. So this inner product, we fix a inner product in V. V is an inner product space. There are infinitely many inner products, as I said, but I fix a inner product, and then with respect to that inner product, I take square root of inner product of V with V, and that is called the length of V. And this definition specializes to our usual definition of absolute value of a complex number, x square plus y square. Okay, and if the length turns out to be 1, we say the vector is a unit vector. Okay, the vector is a unit vector, right? So if C is a scalar, then norm of CV, yeah, norm of CV is square root of, it is square root of CV with CV, but that is equal to square root of CC bar, okay, V with V, and square root of CC bar is absolute value of this complex number, and this is VV. So this is absolute value of C times norm of V. So when I take scale a vector in complex in inner product space, which could be over reals or complexes, then the norm of scaled vector is absolute value of C times norm of the original vector. Okay, yeah. And we say two vectors are orthogonal or perpendicular if their inner product is 0. And this is again lifted from usual dot product of vectors in R2 or R3, that when dot product is 0, then vectors are perpendicular. Now dot product is being replaced by inner product in inner product space. So we will say that two vectors are orthogonal or perpendicular if their inner product is 0. And we will write this as V perpendicular to W. Okay. Yeah. Okay, so we have introduced length of a vector. It is square root of inner product of V with itself. And then we notice that if you scale a vector, then the norm of scaled vector is equal to absolute value of C times the norm of V. And if two vectors are perpendicular, we test it by checking whether their inner product is 0. Okay. Now, length of a vector and angle between vectors, they satisfy some basic properties in Euclidean geometry. Let me show how to prove them. So using the idea of inner product, we will give very fast proofs of some standard results in Euclidean geometry. So let's first look at the fundamental result in Euclidean geometry is Pythagoras theorem. Okay, let us see how to prove Pythagoras theorem in arbitrary inner product space. So you are familiar with Pythagoras theorem in the plane. Yeah, take a triangle in the plane where the base and the height are perpendicular. Then the sum of squares of length of the base and the height is the square of the length of the hypotenuse. So let us see that we have a Pythagoras theorem in arbitrary inner product space, and therefore it implies the Pythagoras theorem in R2. But inner product space could consist of matrices. So we can talk about when two matrices are perpendicular. Yeah, because we have introduced analog of dot product in the space of matrices. So we can measure angle between any two matrices also. We can measure angle between sine x and cosine x. And you will see that the angle between sine x and cosine x is 90 degrees. You may say, how do we visualize that? But it is forced on us. The inner product of two functions, we defined an integral. Okay, an integral of sine x and cosine x on only on 0 to 1 on this closed bound interval is 0. Okay, so we have imported these notions of angle, the perpendicular vectors and length of a vector in arbitrary inner product space, and therefore we can ask whether Pythagoras theorem is true, and the answer is yes. So suppose I have two vectors which are perpendicular in inner product space, then the square of the length of v plus w is the square of length of v plus square of length of w. This is the Pythagoras theorem. Okay, yeah, so let us prove that it is absolutely easy to derive this using the axioms of inner product. Okay, so square of length of v plus w, we by our definition says it is equal to inner product of v plus w with v plus w, but then use linearity in every component. So it is equal to v w w. But the other parts have become 0 because v and w are perpendicular to each other. But the inner product of v with v is this. Inner product of w with w is this. So this is the Pythagoras theorem. Yeah. Is it not surprising? We have a very short proof of Pythagoras theorem. One line proof of Pythagoras theorem. Yeah. Okay. Let's look at the parallelogram law. Okay. Remember the parallelogram law? The parallelogram law, you have in parallelogram, you have a parallelogram. Suppose this is v and this is w, then this vector is v plus w, and this vector is v minus w. This is w minus v, and this vector is v plus w. Okay, so the two diagonals are v plus w and v minus w. So this says that the sum of squares of the lengths of two diagonals is 2 times the square of length of v plus 2 times square of length of w. This is the parallelogram law. And just like this, you can just check, substitute these quantities on the left hand side. You will see that this is true. So here we are not saying v and w are perpendicular. V and w can have any angle between them. Okay, but this parallelogram law, this is true. You can write a very short proof of this. This is an exercise. Now, in the plane, in physics courses, you must have seen that if I have a force vector and I want to see its effect on a moving particle, suppose a particle is moving like this, then to see the effect of the force vector, I have to take a vector in the direction of the movement of the particle and a perpendicular vector. So I have to decompose this force vector into two components. One is in the direction of the movement of the particle, and another is which is perpendicular. And you know that this perpendicular vector has no effect on the motion of the particle. It is this other vector which is in the direction of the particle, movement of the particle, has effect on the movement of the particle. Okay, so in many physical situations, we have to decompose a vector as a sum of two perpendicular vectors. Yeah, so this direction is fixed. This is in some direction. This is some direction w, and this is a vector v. Yeah. Then we want to take a vector which is in the direction of w, and we want to take a vector which is perpendicular to the direction of w, and decompose my vector as a sum of these two vectors. One is in the direction of w, another is in the direction which is perpendicular to w. So this is done by using the notion of projection. We take this vector and we project in the direction of w, and then I get this vector, and then take a perpendicular vector to this, so that their sum is this original vector, and that is the decomposition. Okay,